All right, so we are looking at symmetry of polar equations, but this is going to just be very short and sweet. We're not going to do the algebraic part of this, so that's why we're kind of going backwards. Like yesterday was 6-3, this is 6-2, because if I do 6-3 first, then we can just look at it from a visual aspect from what we already know, which is good enough for us right now. It's not worth the stuff that goes along with it. It doesn't really go with what we're doing. So you do need to know the types of symmetry that go along with your polar curves. So I'm going to ask you some questions that are not necessarily symmetry related. Looking at your reference sheet from yesterday, what is this thing called? Limicon with an inner loop. Good. And then knowing what you know from yesterday, would this be sine or cosine? Sine. And would it be positive or negative? Positive. Beautiful. Okay, so what is this one? What's this? 3-petal rose. Good. Sine or cosine? Cosine. Positive or negative? Positive. Beautiful. What is this thing called? The lemniscate. Okay, sine or cosine? Sine. All right, and whether it's positive or negative, we didn't really go into that with this one. Negative would be over here for sine, so it's positive. Okay, so let's talk about the symmetry then. You can have these functions be these graphs be symmetric to theta equals pi halves, which is like what you would think of as the y-axis, symmetric to the polar axis, which is what you could think of as the x-axis, or symmetric to the pole, which you can think of as the origin, right? So if it's symmetric to theta equals pi halves, that means I can reflect it in that line, and it looks the same. So this one has that symmetry. Symmetric to the polar axis, I can reflect it in the polar axis, and it's going to look the same, okay? The symmetric about the pole is like your origin symmetry when we talked about it with functions. That means if I rotate this 180 degrees, it's going to look the same. So in that case, that means you could just turn your paper upside down. It looks exactly the same. It's symmetric to the pole. Okay? Excuse me. The algebraic tests for symmetry, which like I said, we're not going to do, but I want to at least tell you that they do exist. If I use this equation, okay, and I replace the r and the theta with negative r, negative theta, and then simplify it, if I get the exact same equation that I have right here, then it would be symmetric to theta equals pi halves. If I replace them with r negative theta and I get the same thing, then it's the polar axis. Okay, so that's the algebraic test for it, which for the basic or the classic polar curves that we already know, we don't need to do all that because we have a different way to do it. For other graphs that we wouldn't necessarily know, then we would need to do that unless we knew more about them. But we're just going to keep it classic. All right, so let's look at number 1. It says determine if the graph of the polar equation is symmetric with respect to the line theta equals pi halves, the polar axis, or the pole. So this right here, I have two terms. So that means that I have an A and a B, and in this case, A equals B. And if A equals B, what is this thing? Cardioid. And I realized yesterday during 6th period that I'm pretty sure I spelled cardioid wrong every single time I wrote it yesterday because I started putting in the second I and I was like, that looks weird. I thought, oh, well, it looks weird because I haven't been putting it. So I was just putting cardioid, I guess. I don't know. But nobody stopped me, but it's cardioid. Okay, so based on what we know, so I'm drawing what looks like an x and a y axis, but it's the theta equals pi halves and it's the polar axis or theta equals 0. And we are going to sketch this very, very badly. Okay? I mean, it doesn't have to be bad, but we're not trying to get it even anywhere near how good it was yesterday, and it wasn't that good yesterday. If it is cosine and it's positive, then I know the majority of the graph is over here, so it's going to look something like that. And that's good enough for us to be able to figure out the symmetry part of it, right? Is this symmetric to theta equals pi halves? No. Is it symmetric to the polar axis? Yes. If it was graphed correctly, definitely. Mine, not so much. Is it symmetric to the pole? No. Okay, so based on what you know and how you can quickly sketch it, you can figure out the symmetry. We don't have to go through the algebra part of that. Okay? This doesn't actually match a classic curve. We're going to skip number 2. All right, number 3, what is this called? Lemniscate. meniscus. Okay. And this is cosine, so it would look like this, kind of like infinity. If it was drawn accurately, would it be symmetric to theta equals pi halves? If I reflect it in this line, is it going to look the same? Yes, so it is symmetric to theta equals pi halves. Is it symmetric to the polar axis? Yes. If I reflect it in here, then yes. Is it symmetric to the pole? Yes. If I rotate it 180 degrees, it's going to be the same. So this one happens to have all three types of symmetry, which is totally possible. I know. Okay. So then this one has an A and a B. So here A is greater than B. Remember, there's two of them where A is greater than B. So I have to decide how much greater than B is it. And what would this be dimpled or convex? Dimpled. Okay, so this is a dimpled limison. And it's sine and it's negative. So I know the majority of the graph is going to be down here. And so my dimpled limison would look something like that. Is it symmetric to theta equals pi halves? Yes, it is. Is it symmetric to the polar axis? No. Is it symmetric to the pole? No. If I rotate it 180 degrees, it looks upside down, right? So, why am I marking them? I'm sorry. I said no, and then I marked them off. So it's only symmetric to theta equals pi halves. Okay, make sense? We good? All right, so your assignment today is a worksheet that's not informative because it wouldn't make sense to be informative because you're graphing. But you're going to graph very much like what we did yesterday. That's why I said your notes from yesterday would be helpful too. The only thing you're adding is what the symmetry is. Okay, you still have to put the maximum R value and graph it, but then we add the symmetry to it. Okay, make sense? You should probably be able to finish this today in class, and the key is over there on that table in front of my desk.